In this video, I'm going to talk about charge distributions, general charge distributions. So we have defined how to find electric field due to a point charge, kq by r square. If you have a point charge here, let's say a positive charge, the electric field at this point is equal to k, Coulomb's constant, times the main charge q divided by distance between these 2 points, the whole square, right? If you have 2 more charges, I'm going to add 2 more charges. The total electric field will be the electric field due to charge 1 at this point P plus electric field due to charge 2 at this point P plus electric field due to, let's say this one, charge 3 Q3 at this point P. Okay, if you had two more charges, then plus kq4 by r square plus q5 by r square. What if you have an infinitely long conducting wire with infinite number of charges flowing through it? How do you find the electric field at this point, let's say r, due to this many charges? You can use this equation, but it's quite impossible to find the electric field produced by individual charges at this point r, then add them all to find the total electric field. So we need a new method for that. In this topic, we will modify this equation to find the electric field due to infinite number of charges for different objects, one-dimensional objects, two-dimensional objects, and three-dimensional objects. Okay, I'm going to assume a small portion of this wire, let's say this small part. If the total length is L, let's call this length dl. Let's assume this charged wire has uniform charge density lambda. Lambda is the linear charge density of this wire. How can you define lambda? Lambda is the total charge divided by the total length of this wire. Because it's uniformly charged, you can modify this equation as dq over dl. Total charge in this element divided by the length of this element, which is dl. The total length is L, the length of this small element is dl. Yeah, so that's the equation for linear charge density, lambda equals dq over dl. You can rearrange this equation to find dq. dq equals lambda dl, and we can replace q here with lambda dl to find the electric field due to this small element. So this is for this infinitely long wire, which is a one-dimensional object. If we have a two-dimensional object, let's say a plate with surface charge density, it has area, it's a two-dimensional object. So surface charge density sigma. How do you write the equation for sigma? Sigma is, consider a small area element here. The charge is inside that area element divided by the area element dA. So sigma equals dq by dA. Okay, we can write the equation for a 3D object as well. Let's say sphere. This is a three-dimensional object, so we have to consider the volume. So I'm going to define volume charge density here, rho, volume charge density. And how do you define rho? Again, consider a small volume element. So rho equals charges inside that volume dq over the volume element dv. That is volume charge density. So we have these three equations: lambda equals dq by dl, sigma equals dq by dA, and rho equals dq by dv. Okay, rearrange this equation to find dq. dq equals sigma dA. Rearrange this equation to find dq, rho dv. What is the unit for lambda? Lambda equals dq by dl, right? Unit of q over unit of length. Unit of q is Coulomb, unit of length is meter, so Coulomb per meter is the unit of lambda. And for sigma, it's the surface charge density, it is for a two-dimensional object. Sigma equals q over a. Unit of q is Coulomb, unit of area is meter square. Coulomb per meter square is the unit of sigma. The unit of rho is equal to unit of Q over unit of V, volume, Coulomb per meter cube.